Look closely at the continuity of the ice fracturing around this hull. Early text-to-video models produced brief, morphing fever dreams. This sequence holds physical structure for a full 10 seconds. The architecture driving this stability is outlined in a recent paper from Tsinghua University and Jipu AI, titled CogVideoX. The researchers succeeded in generating continuous 10-second videos at 16 frames per second with a resolution of 768 by 1360 pixels. Prior open-source models struggled to maintain coherent narratives over time. Pushing a generation past a few seconds typically resulted in the geometry of the scene collapsing entirely. They also struggled with complex physics. Characters and objects could barely sustain significant, realistic motion without dissolving into a blur. Finally, semantic alignment was notoriously poor. The generated video would routinely ignore the specific details requested in the user's text prompt. The authors solved these bottlenecks through 3 distinct architectural designs: a 3D causal VAE, an expert transformer, and a progressive training curriculum. By resolving narrative decay, physical distortion, and prompt ignorance, AI video generation transitions from an experimental toy into a viable tool for complex storytelling. Before examining the architecture, we have to look at the training data. Training a diffusion model on raw, unstructured internet video produces chaotic outputs. The researchers built a rigorous pre-processing pipeline. They evaluate clips using motion and aesthetic scoring filters, explicitly discarding static footage and isolating only high-quality dynamic movements. They then process this curated footage through a custom video captioning method. Generating dense, highly descriptive text for every clip is mandatory. The diffusion model relies on these exact textual anchors to map language to visual space. A massive, precisely labeled dataset forms the baseline. If the training data lacks dense semantic mapping, the downstream transformer cannot learn to align prompts with pixels. The primary computational bottleneck in video generation is sheer volume. Processing high-resolution video frames individually quickly exhausts available GPU memory. CogVideoX manages this data load using a 3D causal variational autoencoder, or VAE, designed to compress the video in both space and time simultaneously. This block matrix represents video data, height by width by time. Standard 2D compression processes frame by frame. 3D compression instead shrinks the entire block uniformly along the temporal axis. By analyzing this axis, the VAE identifies background pixels remaining static across multiple frames. These redundant temporal data points are mathematically collapsed into a single dense latent representation, drastically reducing the overall data footprint. Shrinking the temporal dimension actually improves video fidelity. The model devotes its parameter budget to calculating complex movements rather than rendering the same static sky 30 times. The VAE also maintains causality. Typical 3D compression looks ahead to future frames, causing visual artifacts in video generation because the present state becomes contaminated by an ungenerated future. A glowing barrier prevents data from the future from flowing backward. This strictly enforces the arrow of time in the latent space. Each frame is generated based only on the prompt and the exact temporal frames that immediately precede it. Combining temporal compression with strict causal boundaries allows the model to map 10 continuous seconds of video without collapsing the memory limits of the hardware. Resolving the memory bottleneck still leaves the problem of modality fusion. Models frequently drift away from the text prompt during generation. The authors correct this using an expert transformer architecture. Standard cross-attention treats text and video separately. The text acts merely as an external condition, heavily restricting how deeply the two modalities can interact. This diagram outlines the expert transformer approach. We see 2 parallel data streams, text embeddings and 3D video latents, routing directly into a single unified transformer block. Inside this block is a specific module called the Expert Adaptive Layer Norm. It ensures both streams adapt simultaneously, continuously adjusting the video stream's weights, guided by real-time signaling loops directly from the text stream. This creates a tight feedback loop. The linguistic instructions constantly modulate the visual generation at a structural level. Through this structural fusion, specific text instructions, like the trajectory of an object or the shifting of light, are mapped perfectly onto their temporal movements. The expert adaptive layer norm anchors the video latents to the text embeddings, ensuring the initial prompt dictates the physical action across the entire 10-second run. Initializing an untrained model directly onto 10-second high-resolution continuous video results in immediate failure. The parameter space is too vast. The training requires a progressive schedule. The model begins by attempting to generate very short, low-resolution clips. As the model learns basic physical consistency, the training steps up in phases, gradually increasing both the duration and the pixel resolution. To feed this curriculum, the authors introduce a multi-resolution frame pack technique. Traditional video training forces all clips to be cropped into a single uniform aspect ratio. This inevitably destroys edge data and spatial context. This animation illustrates the frame packing solution. Various aspect ratios, vertical, square, widescreen, are Tetris-packed efficiently into a single, uniform processing batch without losing any of their original borders. Retaining these diverse dimensions prevents the model from overfitting its spatial understanding to one rigid aspect ratio. Packing these distinct shapes tightly into uniform batches also maximizes GPU utilization, cutting down the necessary compute time. Progressive training and multi-resolution packing serve as necessary scaffolding, allowing the massive VAE and transformer architectures to converge successfully on a final high-definition target. This bar chart displays CogVideoX machine metric scores. When measuring FVB and VBench metrics against stable video diffusion and previous iterations of CogVideo, we see a stark performance gap in both temporal coherence and visual fidelity. The authors explicitly attribute this accuracy to the strict, dense captioning in the data pipeline and the modality fusion of the expert adaptive layer norm. The model does have operational limits. The frame rate is currently capped at 16 frames per second. Generating smooth, 60 frame per second photorealism over a 10-second duration remains out of reach. Additionally, calculating the 3D VAE and processing the expert transformer exacts a heavy computational toll during inference. Despite the steep hardware requirements, CogVideoX provides a robust solution to temporal degradation, establishing a highly capable open-source baseline for coherent AI video generation. To review the mechanics of the system, first, the 3D causal VAE compresses video space and time efficiently without breaking the arrow of causality. Second, the expert adaptive layer norm binds text embeddings to video latents to solve modality misalignment. Third, progressive training scales these architectures to massive outputs without stalling convergence. For more teardowns of production-grade AI architectures, subscribe and hit the notification bell. Thanks for watching.